Hello everyone. For every linear programming problem that we study, there is an associated linear programming problem called its dual. The original problem is also referred to as the primal problem. Now the primal dual pair are like the two sides of the same coin. So interestingly, while we are solving one of them, we also happen to solve the other one simultaneously. So in this video tutorial, I'll be telling you how to solve one of the problems and obtain the solution of its dual.
For this, let us take up the fundamental theorem of duality first. So, let us see what are the statements of this theorem. The first condition says that if one of the problems, the primal or the dual, is optimal, it would indicate that the other problem is also optimal. Now here saying that it is optimal implies that there is a finite optimal solution, and the objective function values in this case of the primal and the dual would be identical. Now the second statement is, in case our primal or dual, either of them is unbounded, it would imply that the other problem, which is either the dual or the primal, is infeasible. Now here unboundedness means that we have an unbounded optimal objective function value. The third statement says that if one of the problems, either the primal or the dual, is infeasible, that would imply that the dual or the primal problem, the other problem, is infeasible, or it could be unbounded. Now let's see how to read solution of the primal or the dual from the final tableau of the other problem while solving using the big M method. So here we are solving a linear programming problem using the big M method, and by using the fundamental theorem of duality, and we will see how to read the solution of the other problem. So we are solving it now here using big M method. Now just to recall a few concepts, for a maximization problem, the stopping criteria says that whenever Cj minus Zj's are all negative, less than or equal to 0 for all the values of the variable j, then we would stop the problem and we have reached optimality. So, in this case, the value of the dual variables corresponding to the inequality constraints is given by the negative of Cj minus Zj values for the corresponding slack or surplus variables. Now, what does this mean? It means that whenever we have inequality constraints in the primal, we obviously have slack or surplus variables associated with those inequality constraints, and the Cj minus Zj values of those variables, which are the slack or surplus variables, you are going to take the negative of the Cj minus Zj. That would be the value of the corresponding dual variable. So this is how to read the dual variables which correspond to the inequality constraints, given that the problem is a maximization problem. Now in case we have some equality constraints and we are solving the problem by big M method, in that case how to read the dual variables is like this. In this case, we will first solve the problem using big M, and then we take the negative of the Cj minus Zj values for the corresponding artificial variables after ignoring the M term. So how do we find the value of the dual variables? The value of the dual variables which correspond to equality constraints is obtained by taking the negative of the Cj minus Zj values, and we are going to ignore the M term and then take the negative of the remaining expression which we have. So here you would I hope you all know that every artificial variable or every equality constraint will indicate the presence of an artificial variable, and that would correspond to a dual variable which would be non-negative. Now I'll take up the case of a minimization problem. In case of a minimization problem, the stopping criteria is that all the Cj minus Zj's are non-negative, they are greater than or equal to 0, and when we reach such a situation, we say that the optimality has reached. Now in this case, suppose if we want to find the values of the dual variables from the solution of the primal. So in that case, whenever we have dual variables corresponding to inequality constraints, then we are going to take the value of Cj minus Zj as it is for the corresponding slack and surplus variables. So the Cj minus Zj for slack and surplus variables, we would take them as it is, and they would be equal to the value of the dual variables. In case our dual variables correspond to equality constraints, then what do? Then in that case again we take the negative of Cj minus Zj values under the artificial variables in the tableau, and we ignore the m term. So here as well we are going to take the negative of Cj minus Zj values, but we will ignore the m term. So this process is similar to that of the maximization process. The only difference is, in case of a maximization process, when we are talking about the value of the dual variables corresponding to inequality constraints, then we are going to take the negative of Cj minus Zj, and in case of a minimization problem we are going to take the value of the Cj minus Zj as it is. So we are not going to change the sign in this case, but in case of dual variables corresponding to equality constraints, for either a maximization problem or a minimization problem, we are going to take the negative of Cj minus Zj values, ignoring the m term which corresponds to the artificial variables. Now let us see some examples which will explain these points. So this is the first example which I am taking up. So what I am going to do is I am going to solve this maximization problem, and using the conditions which I have just stated, I am going to get the answer of this of the dual for this problem. So let me just formulate the dual as well simultaneously, so that I know which is the problem for which the solution is required to be obtained in the end. So this is my dual. Now here you can see that the first constraint in the primal problem is equality, and therefore the first variable corresponding to that in the dual is an unrestricted variable. The other two variables are non-negative, and we can form the constraints for the dual using the constraints of the primal problem. Now let us proceed with the big M problem. So when we solve this problem using the big M method, this is what our objective function changes to. So we are attaching a coefficient of minus m with the artificial variables. Artificial variables have been attached in the first constraint because it is equality, and in the second constraint, since it is a greater than equal to constraint, we would attach a surplus, and simultaneously we also need to attach an artificial here to get our initial basic feasible solution. And for the third constraint, since it is a less than equal to constraint, we are going to attach a slack variable. So this is our starting problem now when we want to solve it using the big M technique. Now before we proceed with the solution part of this, let us see what is the association between the primal big M problem and the dual problem. So how do we associate the variables? The artificial variables would be associated like this. A1 is associated with the first variable of the dual, which is y1. Then S1, that is the surplus variable in the primal problem, is associated with the second dual variable y2, and S2 here, which is corresponding to my third constraint, is associated with the third dual variable. So A1 from the first constraint corresponds to the first dual variable, S2 from the second constraint corresponds to the second dual variable, and S3 from the third constraint is associated with the third dual variable. So we would now see how to solve this using simplex. So this is the final tableau of the primal problem using the big M technique, and this is achieved at iteration number 4. So in this iteration, you can see here the Cj minus Zj values are either negative or zeros. So all of them are either negative or zeros, and that shows that we have reached optimality. That is the optimality criteria for a maximization problem. The value of the objective function for the primal problem using big M technique is 42, and this is the same as the value of the objective function of the original primal problem, because we do not have any artificials appearing in the basis. So that means the artificials have now left the tableau, and they are not present in the basis, and hence our problem is feasible. It has a finite optimal value, and this optimal value is the same for the original primal problem. So let us see the solution of the primal problem. the primal problem has the values of the basic the variables x1 as 8, x2 is 2 and x3 because it is non-basic, so the value is 0, and the optimal value of the objective function is 42, which is the same as this, because now the objective function no longer contains any terms of a1 and a2, so we just have the original objective function back with us. Now again, just to recall the association, what is the association? For the primal, a1 is associated with the first dual variable y1, again s2 is associated with y2, and s1 is associated with y2 and s2 is associated with y3. So now let us see how to read the dual solution. Now for the dual problem, the optimal basic feasible solution is obtained like this. Since y1 is associated with a1, we are going to look at the Cj minus Zj value for a1. Cj minus Zj value is minus m minus 7 by 2. Now according to our procedure, we are going to ignore the m term, so we are not going to include this term, and we will take the negative of the remaining portion, which is minus 7 by 2. So we are going to take the negative of this, which becomes 7 by 2. So we have our y1 equals to 7 by 2. Now next is y2. y2 is associated with s1. So let us look at Cj minus Zj of s1. It is 0 in this case. So the value of y2 is also 0. For y3, since y3 is associated with s2, we are going to look at the Cj minus Zj for s2. This is minus half, and according to our rule, we are going to take the negative of this. So y3 will become positive half. So these are the values of our dual variables for the dual problem corresponding to the primal which we have solved here, and the optimal value of the objective function is 42, which is the same as that of the optimal objective function value of the primal problem. So whenever we have seen in the rule that whenever the primal is having a finite optimal value, the dual will also have a finite optimal value of the objective function, and both the values will be identical. Okay. So this is how you can read the solution of the dual problem by solving the primal. This is the case of maximization. Now I will consider another case, which is a minimization problem. So we have here a minimization problem which has again a mixed set of constraints, a greater than equal to constraint, a less than equal to, as well as an equality. So corresponding to this is my dual problem. So here again I have all less than equal to constraints, and my objective function is a maximization function, and the third variable is unrestricted because here the third constraint is an equality constraint. So once we have constructed the dual problem, let us now start solving the primal using again the big M method. So this is the primal problem using the big M method. Now since this is a minimization problem, we are going to attach coefficients plus m along with the artificial variables. Artificial variables are present in the first constraint being a greater than equal to constraint, and in the third because it is a equality constraint. So now let us see also the association between the primal and the dual. Now since the first variable here in the dual corresponds to the first constraint of the primal, and in the primal the variable which is present here is s1. So s1 is associated with y1. Now the second dual variable y2 is associated with the second constraint. In the second constraint we have this slack variable s2. So this is our association, s2 associated with y2. In the third constraint we have this dual variable y3 corresponding to the third constraint, and the third constraint has the artificial variable a2. So this is our correspondence, a2 corresponding to y3. Now let us see how to get the solution of the dual by solving the primal using big M technique. So we have again the final tableau in front of us. This is again achieved at iteration number 4. Here we notice that all the Cj minus Zj's are greater than or equal to 0. You can notice that, which indicates that optimality has reached and we need to stop here. Now the optimal value of the objective function here is minus 2, and since no artificial variables are present in the basis, so it would be same for the original primal problem as well. So let us see what is the a solution to the original primal problem. The solution to the original primal problem is this: x1 is 32 by 15, x2 is 1 by 3 and x3 is 1 by 15, and the objective function value is -2, the same as objective function value achieved here, since artificials are not present in the basis. Now again we will recall the association S1 with Y1, S2 with Y2 and A2 with Y3. So let us see how to predict the solution to the dual problem. Now since Y1 is associated with S1, we are going to look at the Cj minus Zj corresponding to S1, which is 7 by 4. So we will take it as it is, since it is a minimization problem. Now corresponding to Y2, the variable is S2, and for S2 Cj minus Zj value is half, so Y2 will also be half. It will be the same value again, since it is a minimization problem. Now Y3 corresponds to the artificial variable A2. So let us look at Cj minus Zj for A2. It is m plus 1 by 4. Now for this, what do we have to do? We have to just ignore the m term. So we will just remove this term, and the remaining portion we are going to take the negative of the remaining portion. So we are going to take minus 1 by 4 here. Okay. So we are going to take Cj minus Zj of the artificial, remove the m term, and then take the negative of the remaining expression, which comes out to be minus 1 by 4 in this case, and that is the value of the variable y3, the dual variable y3. So this is how we can get the values of the variables in the dual problem, and objective function value for the dual is the same as objective function value for the primal, which is -2. So that is how we can read the objective function value.
So in case the linear programming problem at hand involves a large number of variables and its dual is comparatively easier to solve, you may use these set of rules, solve the dual and obtain the solution to the more complex primal. So bye for now and take care.